Almost everyone has once had fun arranging dominoes in a series and starting a wave. Push the first domino and it topples the second. The second will topple the third, and so on and so forth until all the dominoes are toppled. Now let us change the set of dominoes into an infinite series of propositions P1, P2, P3 and so on, numbered by positive integers. Assume that we can prove the first proposition of the series is true. The truth of every proposition in the series implies the truth of the next one. Then in fact, we have already proved all the propositions in the series. Indeed, we can push the first domino, that is, prove the first statement B, and then statement S means that each domino in falling topples the next one. Whatever the domino or proposition we choose, it will eventually be hit by this wave of falling dominoes, or what we called proofs. This is a description of the method of mathematical induction. Theorem B is called base of induction and theorem S is the inductive step. Our reasoning with the wave of falling dominoes shows that the step S is nothing but a shortened form of the chain of theorems shown on your screen. We will call theorems in this chain steps and the process of the successive proof the process of induction. The process can be visually represented as a wave of proofs running from statement to statement along a chain of theorems. Psychologically, the essence of induction is in its process. How can we teach this? We will try to show this to you in a dialogue between teacher and student.
Hello, Victor. Well, I have a problem for you. Would you like to give it a try?
Why not? I am excited.
Okay. One box was cut off from a 16 by 16 square of a graph paper. Prove that the figure obtained can be dissected into dominoes of a certain type. Let's call them corners.
But this is easy. Any corner has 3 boxes and 16 square minus 1 is divisible by 3.
If it is so easy, could you cut a 1 by 6 band into corners? 6 is also divisible by 3.
Well, actually, I should not have said that. I don't exactly know how to solve this problem.
Okay, you cannot solve this problem. Perhaps you can think of another problem which is similar yet easier.
Well, you can take another square of smaller size, say 4 by 4.
Or 2 by 2.
But there is nothing to prove in this case. When you cut out any box, what you get is just a corner. What sense does that make?
Try now to solve the problem about the 4 by 4 square.
A 4 by 4 square can be cut into 4 2 by 2 squares. It is clear what to do with the one with the cut box. What about the other 3?
Try to cut a corner from them, located in the center of the big square.
Got it. Each of them would lack one box and turn into a corner. So we can solve the problem for a 4 by 4 square too. Now,
try an 8 by 8 square. It can be dissected into 4 4 by 4 squares. Make use of this.
well, we can reason as we did before. One of those squares has the missing box in it, and we have already proved that this one can be cut into corners. The other 3 squares will lack one box after we cut one corner in the center of 8 by 8 square. So we will be able to dissect them too.
Do you see now how to solve the original problem?
Sure, we cut the 16 by 16 square into 4 8 by 8 squares. One of them contains the cut box. We have just proved that it can be dissected into corners, right? Then we cut out a corner in the center of a big square and we get 3 more 8 by 8 squares, each without one box, and each can be cut into corners. That's it.
Not yet. We solved this problem by building bridges from similar but simpler questions. Could we build such bridges once more to other more complicated questions?
Of course, let us prove that one can dissect a 32 by 32 square into corners. We just divided mentally into 4 16 by 16 squares.
There you are. But is it possible to go further?
Certainly. Having proved the proposition for a 32 by 32 square, we can now derive in the very same way the method of dissection for a 64 by 64 square, then for a 128 by 128 square, and so on.
Thus, we have an infinite chain of propositions about squares of different sizes. Can we say that we have proved them all?
Yes, we have. First, we proved the first statement in the chain about a 2 by 2 square. Then, we derived the second proposition from it. Then the third from the second, etc. It seems quite clear that going along this chain, we will reach any of its statements. Therefore, all of them are true.
Right. It looks like a wave of proofs running along the chain of theorems from 2 by 2 to 4 by 4 to 8 by 8 and so on. It is quite evident that the wave will not miss any statement in the chain.
Alright, this was the first part of the conversation. The teacher here has played his part precisely. Sometimes he leads away from a deceptive analogy and helps to save the student's energy. Unobtrusiveness is very important. The more the student does on their own, the better. Let us sum up the results. The student, but more often this is the responsibility of the teacher, explained the scheme of the method of mathematical induction. The underlined sentence, "Going along this chain we will reach any of its statements," is nothing but an informal statement of the principle of mathematical induction, which is the cornerstone of method of mathematical induction. We must say though, it would not be wise to talk about this at the very beginning of the discussion. It may be premature or even harmful, since formalization of this intuitively clear statement may give rise to feelings of misunderstanding and uncertainty. On the contrary, one must use all means to make the scheme as evident and vivid as possible. Aside from the wave and dominoes, other useful analogies include climbing a staircase, zipping a zipper, etc. We will continue with our teacher-student discussion in the next video to see how the generalization looks mathematically. Until then, goodbye, take care and keep learning.